Buongiorno, io sono Gaia e faccio parte di WeScience, il gruppo giovani di Bergamo Scienza. Le conferenze della 23esima edizione di Bergamo Scienza sono rese accessibili a persone con disabilità motorie e sensoriali, garantendo luoghi privi di barriere architettoniche e servizi di traduzione LIS. Tutte le conferenze sono videoregistrate, alcune delle quali sono anche trasmesse in diretta streaming. Le conferenze con ospiti stranieri prevedono la traduzione simultanea. Le registrazioni verranno pubblicate sui nostri canali ufficiali al termine del festival. Questi servizi sono resi disponibili grazie a Fondazione della Comunità Bergamasca e Fondazione Banca Popolare di Bergamo, che insieme a Bergamo Scienza sono impegnati a promuovere inclusione e accessibilità. Per la traduzione simultanea è sufficiente scannerizzare il QR code che vi possono fornire i nostri volontari in sala o che trovate proiettato alle mie spalle. Il QR code vi indirizzerà direttamente a Converso Web App, dove potrete selezionare la lingua di interpretariato dal menu a tendina. Per l'ascolto della traduzione è necessaria una coppia di auricolari. Vi chiediamo la cortesia di utilizzare le vostre. Chi ne fosse momentaneamente sprovvisto può chiedere ai volontari in sala. Vi ricordiamo anche che alle ore 17 ci sarà l'incontro moderato da Daniel Bonazzi della Fondazione Bergamo Scienza, con introduzione di Giovanna Recuperati di Confindustria Bergamo e l'intervento di Anna Grastellino del Fermilab, che ci racconterà il mondo dei computer quantistici, spiegando come questa tecnologia rivoluzionaria potrebbe trasformare la crittografia, l'intelligenza artificiale e la scienza e di quanto siamo vicini a renderla realtà. Vi do ora il benvenuto all'evento di questo pomeriggio, intitolato Il sogno dell'energia infinita. Avremo il piacere di ospitare come relatrice Rachel McDermott del Max Planck Institute for Plasma Physics. La conferenza sarà moderata da Gabriele Beccaria della Stampa Gruppo Gedi. Vi preghiamo ora di silenziare i vostri apparecchi elettronici e di partecipare numerosi alle iniziative di Bergamo Scienza. Grazie per l'attenzione e buon ascolto.
Grazie di questa presentazione, buonasera, grazie a Bergamo Scienze e a voi tutti di essere qui. Come è stato detto, oggi abbiamo il piacere di avere la professoressa Rachel McDermott che dirige l'istituto Max Planck per la fisica del plasma e capiremo dalla sua presentazione che adesso ascolteremo perché il plasma è così fondamentale nella tecnologia della fusione nucleare. Oggi parleremo di un tema che è fondamentale per tutti noi e non a caso è stato scelto questo titolo che solo apparentemente è visionario. Costruire una centrale a fusione nucleare significa in qualche modo portare un piccolo sole sulla Terra e disporre di un'energia pulita e pressoché illimitata. E tutti ormai ci stiamo rendendo conto di come l'energia sia fondamentale per la vita di tutti noi. Stiamo entrando ormai nell'era dell'intelligenza artificiale e se voi guardate i dati scoprite come i server che fanno funzionare le reti neurali richiedano una quantità di energia straordinaria, spesso pari a quella che fa funzionare una piccola città. Quindi l'energia del presente e quella del prossimo futuro sarà determinante per creare il progresso e l'innovazione che tutti noi ci aspettiamo. E quindi direi di ascoltare subito la professoressa con questa sua presentazione e poi avremo una seconda parte di questo pomeriggio con le domande che naturalmente dal pubblico immagino saranno numerose. Prego professoressa e benvenuta e grazie.
So, does this work? Good afternoon, everybody. It is my pleasure to be here today and to have this opportunity to speak with all of you about magnetic confinement fusion research and exactly where we are on the path to fusion energy on Earth. Now, today I would like to try and answer for you 5 questions. First, what is fusion? Second, I would like to clarify the difference between fusion and fission. Third, I'd like to make the case for fusion. Why do we want fusion energy on Earth? Fourth, I'd like to explain how do we create fusion on Earth, and finally, where are we on the path to a fusion reactor? So by the next 45 minutes or so, I hope that everyone here will be able to walk away with the answers to those 5 questions. And I'm going to go ahead and add a caveat right now, which is that in 45 minutes, I cannot possibly give you a 100% complete explanation of these 5 things. So there are going to be plenty of things for us to discuss in the Q&A. So please have your questions ready. I would love to discuss. So with no further ado, I'd like to start with what is fusion? Well, fusion, quite simply, is the energy of the sun and the stars. And it also has the potential to be a clean, competitive, and nearly unlimited source of energy on Earth as well. The sun is composed mainly of hydrogen atoms, which, due to the extremely high temperatures, exist in a plasma state. So what does this mean? It means that at the temperatures that exist in the sun, that electrons are no longer bound to atomic nuclei, as I show here in the case of a hydrogen gas. Rather, they have enough energy to separate from those nuclei. And what you end up with in a hydrogen plasma is basically charged particle soup. So those nuclei are positively charged, the electrons are negatively charged, and they can move relatively independent of one another. Now, if there is enough available energy, then the positively charged nuclei can also collide, and they can fuse together to form a new, heavier element. And that process, the merging of 2 light nuclei to form a slightly heavier nucleus, is fusion. And that is the process that powers the sun, because in addition to just forming a new element, which is already pretty amazing, that process releases a significant amount of energy per reaction. And this comes about because in fusion processes, the masses of the final products are always less than the masses of the starting products. And that mass difference between the starting and the final products is released as kinetic energy of the final products according to Einstein's famous formula, E equals mc squared. So that, in a nutshell, is what fusion is. Let's take just 2 minutes to discuss why this is a fundamentally different process from fission. As we just saw, fusion is when 2 light elements collide and form a heavier element. So on the left-hand side here, on the top left, I give an example of the most common fusion reaction that is envisioned to produce energy here on Earth. This is the DT reaction, where the D here stands for deuterium. This is heavy hydrogen, which means in the nucleus here you have a proton and a neutron. And it can combine with tritium, which is, again, even heavier hydrogen. This is 1 proton and 2 neutrons. They can have a fusion reaction that produces helium plus a neutron. And one thing that is important to note here is that the reactants on the left-hand side, these nuclei are positively charged. And you might have heard that opposite charges attract and like charges repel. Well, these have the same positive charge, and so they actively repel one another. Said another way, fusion reactions don't happen by accident. You have to work very hard to get exactly the right conditions for these reactions to happen at all. Now, in comparison, I have a fission reaction, a typical example of a fission reaction on the right-hand side. And here you use a neutron to break apart a heavy element, in this case uranium, into smaller pieces. And that neutron does not have a charge, which means it has no problem penetrating into this atomic nucleus. There is no force that keeps those things apart. And the reaction produces 2 more neutrons. And this is why in a fission reaction, you have the opportunity for a chain reaction where this fission can happen more and more and more. And that just does not exist on the fusion side of this slide. Now, in both cases, The energy is won from the mass difference. If you were to check with your periodic table of elements, the masses on the left-hand side of these equations compared to the right-hand side of these equations, you will find that the total masses of the final products are always lighter. And that mass difference, again, is being released as energy, E equals mc squared. And so this is the same in the two of them, but there are important differences here. In fusion, there is no such thing as critical mass because the reactants are positively charged particles. They do not result in the production of unstable nuclear elements. There is no direct radioactive waste, but it does produce a neutron, and I'll come back to that on the next slide. Now, in fission, because the neutron is not charged, there is a critical mass problem, and that spent nuclear fuel and the byproducts of these reactions are radioactive with very long decay times. And this means that the waste from a fission reactor remains radioactive for thousands of years. And you can see that here on the right-hand side in this plot, where I show the radiotoxicity index for nuclear reactors. This is as a function of time after the reactor shuts down. And this red line at the top, that corresponds to a fission reactor. And you can see that these things will stay radioactive for a very, very long time. Now, the fusion equivalents, the fusion equivalents are these curves down here. And the neutrons that are produced in a fusion reaction will cause activation of the walls, which means on day one, the walls of this reactor are just as radioactive as in fission. But the difference is in the materials themselves, because the materials, if chosen appropriately, will cool down with half-lives that are very, very fast, such that on the order of 50 or 100 years, these materials become recyclable. So it is not true that fusion does not have radioactive waste. We do. The walls of the reactor will become radioactive, but the half-lives are short. So we do need storage of materials, but you do not need long-term storage. And this is the main difference between the radioactive waste from fission and fusion. Okay. So this brings me to my third question, which is why do we want fusion reactors at all? And the first reason is that nuclear energy offers clear advantages over chemical energy. So let's consider just for a moment a simple model of an atom. Here I have sketched a carbon atom in the top left. You have 6 positively charged protons in the nucleus, 6 neutrons, and this thing has the size of about 10 to the minus 15 meters, or 1 Fermi. And it is surrounded by a cloud of valence electrons, that's about 10 to the minus 10 meters, or 1 angstrom. So you will note that my sketch is not exactly to scale. Now, we can also consider the fundamental forces of nature and how they are at play in this kind of a system. And first we have the strong force, and this is the force that binds the protons and the neutrons of the nucleus together. The second force is the weak force, and this is the force that comes into play in radioactive decay. For example, when a proton becomes a neutron, and this is an important process for fusion in the stars. And then the third force is the electromagnetic force, also known as the Coulomb force, and this binds atoms together. So this is the force that binds the negatively charged electrons to the positively charged nucleus, and it is also the force that is responsible for those like nuclei, the nuclei with the same charges, to repel one another. And then finally, there is the gravitational force, which binds solar systems together, and it's also the force that provides the confinement in the sun, which allows fusion to happen there. But I'm supposed to be comparing chemical and nuclear energy, and when we are talking about producing energy from fossil fuels, so the burning of oil or coal or wood, we are talking about the rearrangement of electrons. So we are playing with the electromagnetic force acting over a few angstroms. So these are ionization energies, and you typically release about 1 electron volt per reaction. In comparison, when you are playing with nuclear reactions, whether it is fission or fusion, you are dealing with the strong force acting over a few Fermi. You are changing the nuclei of these atoms. And this means you are automatically dealing with the release of mega electron volts per reaction. This means nuclear reactions are 10 to the 6 times more efficient than chemical reactions. We get 10 to the 6 times more energy per unit of mass burned. To make this more intuitive, a single spoonful of liquid deuterium-tritium, which is that fusion fuel, would release the same amount of energy as 143 barrels of oil or 28 tons of coal. In addition, there are no greenhouse gases associated with these processes. So it's extremely more efficient and no greenhouse gases. These are the main advantages of nuclear over chemical reactions. Now, let's consider how we are presently meeting our energy needs here on Earth today. Here on the right, I have a slightly older plot from the US Energy Information Administration. It doesn't matter that this is a few years old because the new plots look exactly like this one. And what we see here are two things. One, the world energy usage is predicted to increase as a function of time. And two, the energy demands are by and large being met by the burning of fossil fuels. That is these top 3 curves. This is oil, this is coal, and this is gas. While renewables and nuclear energy do not make up a dominant component of the worldwide energy mix. And so the burning of all of these fossil fuels is having dramatic impact on our environment, on climate change. And you can see that, for example, in this curve here, which is a really, really interesting plot. What you see is the concentration of CO2 in the atmosphere over the last 1,000 years or so. And it was flat at about 280 CO2 molecules per million air molecules from 1000 AD until 1769. And then you see this thing start to increase dramatically. Why? In 1769, James Watt presented the steam engine. And he revolutionized industry. We have revolutionized transportation across the globe. And as a result, we started releasing CO2 into the environment. And so it's hard to look at a plot like this and come to any other conclusion than that the actions of man have increased the amount of CO2 in our atmosphere. Today, we are at over 400 parts per million. Now, I'm supposed to be talking about fusion and not about greenhouse gases, so in the interest of time, I'm just going to say that there is strong scientific consensus and understanding that this has led to a warming of the Earth, significant environmental impact, and this also now has wide political recognition, which led to, for example, the Paris Climate Accords, which targets holding the global average temperature to below 2 degrees, the increase below 2 degrees, significant reduction of CO2 emissions to get to net zero by the middle of the 21st century. And this motivates the development of alternative energy sources, and quickly. So, how does fusion contribute to fighting climate change in the next 20 years? This is a question I get a lot. And the answer is we don't. I'm sorry, I would love it if we could, but we don't. And let me explain why, because I know that's a little disappointing. The first fusion power plants, which will really be technology demonstrators, are targeting a time frame between 10 and 20 years from now, depending on exactly how ambitious a particular group is that is proposing this reactor. So we are looking at between 10 and 20 years for the very first power plants. Maybe there's 1, maybe there's 2, maybe there's 3. But 3 power plants are not enough to make a difference on climate change. What you would need is a fleet, a global fleet of fusion reactors that take over the energy production that is presently being met by the burning of coal and gas and oil. And that is simply going to take longer than 10 or 15 years to develop that entire global fleet. So, will we help stop the global temperature increase by 2040? No. I'm sorry, we won't. So what good is fusion? Why bother with fusion at all if we're not going to help in the next 10, 20 years where we need it the most? Why not just do it all with renewables? Well, you know what? Renewables are great. I have nothing against renewables. They can help a lot. They do help a lot, particularly when you combine them with storage. So yes, absolutely, we ought to invest in renewables. But there is a fundamental limitation to renewables, and that is the intermittency problem that is very difficult to get around. And to demonstrate that problem, we can look at the electricity production in Germany from 2024. You could do this for any year. I just took 2024 as an example. And let's compare a month in the summer, say May, to a month in a more winter month. Let's take a look at November. In the month of May, we have a lot of solar production. That yellow bit here, this is the electricity production from the sun. In green, you have the wind production, and then these sort of brownish colors down here, that's the burning of coal and fossil fuels. Now, the black line at the top is the demand. That's how much electricity was actually used in Germany in these months. And in summer, you can see that the German investment in solar and wind, which accounted to, by the way, for tens of billions of dollars, has paid off with a very high fraction of the present energy demand being met by renewable energy. There is even 1 week here where there is an overproduction. So that overproduction could be combined with storage to maybe also cover the nighttime use. So the daytimes are always the peaks, the nighttimes here are always the trough. But for most other weeks, even in summer, even with the massive investments of wind and solar, Germany does not produce enough energy to cover its own demands, as you can see here. So for that time period, Germany is an energy importer from other countries in Europe. And if we look at November, you suddenly see that solar does not make a contribution to the energy mix in winter at all. It's basically negligible, but you do get significant contributions from wind at the end of November. But there were several weeks at the beginning of November where the wind didn't blow at all. And here, what do you do? What Germany did was to double the amount of fossil fuels that it burned to try and help cover that gap where it had no renewables, but it's also not enough. And Germany ended up importing significant energy to meet its energy demands. So the takeaway messages here are that renewable energy sources can and do make significant contributions to clean energy, particularly efficiently if you couple them with efficient storage, but they suffer fundamentally from intermittency, which means the sun does not shine at night and the wind does not blow 365 days a year. The data also demonstrates the importance of having a base load to meet demand, and we are presently using fission and the burning of fossil fuels for that. And we think that fusion reactors are a prime candidate to replace the burning of fossil fuels and fission to meet those gaps when renewables are simply not available. Okay, so with that, that is the third part of my talk, and I'd like to come to part number 4. I should have a good 20, 30 minutes at least left to talk about fusion, and I'd like to start with how do we create fusion on Earth? So, in the sun, the main process in the sun is known as the PP chain. This is a proton-proton chain. I'll give you an idea of what this reaction looks like down here in the right-hand corner of the slide. This is 2 protons that come together to form a deuterium. And then that deuterium that is formed, it can go on to have additional fusion reactions, forming helium and lithium and moving on up the periodic table of elements. But this first reaction is important because it is so improbable. This reaction requires the weak force. It requires a proton to become a neutron by beta plus decay. And this reaction almost never occurs. It's hugely improbable. But in the sun, the improbability of this reaction is balanced by the sheer number of particles. There are so many particles there that even though it's hugely improbable, it happens often enough that the sun continues to burn. And in fact, this is a super good thing, because if this reaction were more probable, the sun would have burned through all of that mass much more quickly, and there would be no life on Earth. So we should be very happy that this reaction is so improbable. But it also means that this reaction is useless for fusion energy on Earth. We can't take one-to-one what happens in the sun. We need a reaction with a much higher probability of occurring. And up here at the top, I show on the y-axis the probability of a reaction to occur as a function of the interaction energy. And what you see is the DT reaction that I've already mentioned. This is 10 to the 24 times more probable than the proton-proton chain. And this is one of the reasons that we like DT. But DT is not the only fusion reaction that has been considered. It's just the best. And we can see the reasons for it here on this slide. There are 4 reasons why DT is the reaction that is preferred. And the first, again, here I plot the probability of reaction versus energy, and you can see that the DT curve, shown in blue, is the highest of all of these reactions that have been considered, and it is accessible at the lowest energies. So moving from left to right, you hit the blue line first. So that's 2 reasons why we like it. The third reason is that it releases a significant amount of energy per reaction. As you can see on the left-hand side, we get 17.6 MeV per reaction. And finally, it has very nice products. It produces a helium particle here, and it produces a neutron. And that neutron carries 14 MeV. It's extremely useful because you can use the neutron to breed tritium, as I'll talk about in the next slide, and also to produce electricity. And a reactor is not very good unless you have a way of producing electricity. And in a DT reaction, this is how you do it, similarly to in a fission reactor, which also produces neutrons that you slow down, use the heat from those neutrons to boil water, to turn turbines to produce electricity. You do it the exact same way with a DT fusion reactor. Okay, so we like the DT reactor. Basically, every credible company and public program in the entire world is targeting the DT reaction for its fusion power plants. And in order to do so, you need a supply chain. You need to have availability of deuterium, and you need to have availability of tritium in order to have a successful reactor. And deuterium is easy. It's relatively abundant in the ocean water. It can be extracted from the ocean. Estimates would suggest we have something like 10 to the 10 years of deuterium available on Earth. So even if those numbers are a little bit off, we're mainly okay for the foreseeable future. But tritium, on the other hand, is significantly more difficult. It is radioactive with a half-life of about 12 years, and it is not naturally occurring. Rather, the supply of tritium that we have right now comes from fission reactors, and there are relatively few fission reactors that are equipped to produce tritium for civil use. Now, this is something that might change. It's already starting to look like it will change in the world picture as there is a larger and larger demand for tritium for civil use as we are moving towards building these fusion reactors. But at the moment, that bit of the supply chain doesn't exist. But the long-term plan, in any case, is not for fusion reactors to be dependent on fission reactors for its fuel. Rather, fusion needs to be self-sufficient. So a fusion reactor will employ a piece of technology called a blanket, which would surround the reactor. It is lithium-rich, and that blanket would act as a moderator, slowing the neutrons down so that you can use that heat to produce electricity, but also breeding those neutrons with lithium to produce tritium via the reactions that I list here. And tritium is, in fact, very abundant and widespread in Earth's crust and in the ocean water. Rough estimates would again indicate that there is enough lithium for this process for several thousand years. Now, I talk about breeding blankets and moderating these neutrons and producing tritium like this were easy, but the reality is that this technology has never been tested. There are ideas for this technology, but many of these pieces are still in very early stages of development. So the study of fusion materials, breeding blanket design, lithium enrichment, fusion fuel cycles, these are all big, open, major research areas that we are pushing on very hard within the scientific community to have these things established as much as possible as we come to the actual building of fusion reactors. Okay, so how do we build a fusion reactor? Now, for that question, you need to ask, what is it I need to accomplish in order to have fusion happen? And what you need to do is to get that deuterium and tritium positively charged nuclei to touch. You need to get them to within 10 to the minus 15 meters of one another. And you have the problem of the Coulomb barrier, which I have already mentioned. They are positively charged nuclei, which means they will repel each other. So you need to overcome that electromagnetic force to get them close enough that they will, in fact, fuse. And classically, to do this, you would need to accelerate these particles to hundreds of kiloelectron volts, and that's a lot of energy. However, very, very lucky for us, there is a quantum mechanical effect called quantum tunneling that comes into play and actually enables these nuclei to come within 10 to the minus 15 meters of one another at significantly lower energies, at tens of keVs, opposed to hundreds. And you can see that here in the bottom right-hand plot, where this dt cross-section and the dd cross-section, they start to increase, not at 400 or 500, but already down here at 5, 10, 20 keV. So these are the energies you need to reach to have a finite probability of a fusion reaction. You need to get to about 20 keV. This is the equivalent of 200 million degrees. So to build a fusion reactor, the challenge is to take a hydrogen gas and you need to heat it up to 200 million degrees. And if you can do that in a controlled way, then it will start to fuse. It'll start to have these reactions. It'll start to produce those 14 MeV neutrons. Now, when you're dealing with 200 million degrees, as you can imagine, we are no longer dealing with hydrogen gas. We are now, again, dealing with hydrogen plasma. So fusion physics is plasma physics. That's why my institute is the Max Planck Institute for Plasma Physics. And plasmas might sound a little exotic. People are not used to dealing with them as a concept. And if that encourages you to join the fusion team, all the better. But in fact, you encounter plasmas in your daily lives much more often than you might think. More than 99% of visible matter in the entire universe is in the plasma state. I guarantee you, you have encountered plasmas in your daily life. So how do we build fusion reactors? How do we get to 200 million degrees? There are two main concepts that are being followed in the fusion communities. The first is inertial confinement fusion. In the inertial confinement fusion process, what they seek to do is to take a small 1 millimeter pellet of frozen DT fuel, and they fire lasers at it from all sides, ablating the surface of that pellet and causing the pellet to compress. And if you can do this sufficiently well and sufficiently uniformly, then you can get the core of that DT pellet up to the required 200 million degrees, at which point you initiate a fusion burn in the core of that pellet, which then burns up the rest of the pellet from the inside out, releasing a burst of 14 MeV neutrons. And that entire process takes about 1 nanosecond. And then you would need to be able to repeat that process something like 10 times per second, over and over and over, 10 times per second, in order to get a reasonably steady supply of energy. Now, the other side, the other way to do this, is known as magnetic confinement fusion. And here, the aim is to confine a 20 keV, or 200 million degree plasma, in steady state using a magnetic bottle. So magnetic confinement fusion is by far the most advanced fusion reactor concept. And this is the research that I am involved in. This is the research that my institute is involved in. And hence, this will be the focus for the rest of this talk. So magnetic confinement fusion relies on the fact that we are dealing with plasmas. So we have charged particle soup, and charged particles respond to and can be confined by magnetic fields. Our theory of electricity and magnetism has shown that charged particles in the presence of a magnetic field experience a force called the Lorentz force, which I show here. This is, in fact, the only equation that I have included in my entire talk. And this force, the Lorentz force, causes particles to gyrate. Oh dear, I have a spinning circle. Well, let's see if it comes. This force causes particles to gyrate around magnetic field lines. In this way, the particles are confined perpendicular to the field lines, but unconfined in the parallel direction. There we go. A bit of a delay. are confined perpendicular to field lines, but they are unconfined in the parallel direction, so along the field lines. So by closing the field lines on themselves in a donut-shaped geometry, we can create a magnetic bottle that would keep those particles confined, allowing us to heat them up to 200 million degrees without them ever coming into a contact with the wall. And the stronger the magnetic field, the better the bottle. Now, there are two main types of bottles that are widely considered to be good enough bottles that you could build a fusion reactor from that geometry. On the left, we have the tokamak, which has a fairly simple set of coils, as you can see on the bottom down here. So the red coils, these are known as your toroidal field coils. You can put a current in these toroidal field coils in this direction, and that will create a magnetic field that goes around in this toroidal direction. In addition, you have what are known as poloidal field coils, these light blue guys. Those coils are there for shaping and control. And then finally, you have this purple coil in the middle of your tokamak. It's called your central solenoid, and it is there to drive a current in the plasma itself. And this creates an additional component to the field that is necessary for confinement. Now, all of those coils are fairly simple to build, and that's why we say that tokamaks are easy to build. In fact, it's also rather challenging. But the fact that they are fairly simple to build is the reason why the tokamak is the most well-developed fusion concept, and it's the most well-researched fusion concept. There have been the most tokamaks compared to any other fusion concept that have actually been built. So to date, tokamaks boast the best plasma confinement. They are the best bottle. And for that reason, there are public programs all over the world, including Europe, China, Japan, Korea, the UK, who are all building fusion reactors based on the tokamak concept. Now, the second option is the stellarator. And here you can see on the right-hand side that these coils, these blue guys, are significantly more complicated. They are bendy, they are twisty. And so this is why I say tokamak coils have simple geometries, because the geometry is simple compared to a stellarator. And because stellarators are harder to design and they are harder to build, there have been significantly fewer stellarators existing in the world, and they are less well-researched compared to their tokamak brethren. But the stellarator does, in fact, offer good enough confinement that you could build a reactor based on it, and it offers several advantages over a tokamak-based reactor that make it very interesting to pursue, even though they're harder to do. So coming back to this, I mentioned this purple coil in the middle, the central solenoid, that drives a current in a tokamak plasma. And that is necessary for confinement, but it presents two big problems with tokamaks. And one is that they are not steady-state devices. They are inherently pulsed devices. Now, the pulses could be hours long, but at some point, you have to ramp a plasma current up and you have to ramp it back down. And that's maybe not a nice feature that you want in a reactor that should perhaps run 24/7. And it also introduces mechanical strains and stresses from the thermal cycling of this reactor that you maybe don't want to have. And the second problem is that if you have a current, you can have a current quench. So you can have a termination of that current that happens on very fast timescales. And this can actually lead to significant damage to your reactor. You can break your machine, which is obviously also something that you don't want to have happen in a reactor. Okay, I'm speaking too quickly for my poor translators. Apologize, I will slow down. So you can have a current quench, and this can lead to something called a disruption in a plasma, which can lead to strong forces and can lead to damage to the device. Now, the stellarator concept does not have a plasma current. The entire magnetic field is 100% produced by these external coils. So it is inherently a steady-state device, and since it doesn't have the current, it can't have a current quench. And for these two reasons, the stellarator offers advantages over a tokamak when you are looking to build a reactor from these concepts. And my institute, the Max Planck Institute for Plasma Physics, we are actively engaged in research on both of these topics. We operate both tokamaks and stellarators, and are trying to develop the physics basis to build reactors via both of these concepts. So, in Garching by München, we operate the ASDEX upgrade tokamak. This is a medium-sized device. On the right-hand side here, you can see inside of this machine with people walking around, so that'll give you the idea of the size of this donut. And this machine, so this empty area here, this would all be pumped down, evacuated when we have plasmas. And this empty area, that's where the plasma will form. And this donut is actually situated smack in the middle of the mess that you see on the left-hand side. You can't see the tokamak, but it is in the middle. But what you do see all around are the heating systems that allow us to heat the plasma up to 200 million degrees. You also see auxiliary systems, for example, pumps and fueling systems and control systems and diagnostics. So ASDEX upgrade is 30 years old. This is not a young machine. It has copper coils, and the fact that it has copper coils means it's limited to a pulse length of about 10 seconds. Modern tokamaks with superconducting coils can get to significantly longer pulse lengths than that. So here is a video of a plasma in ASDEX upgrade. You can see, what you see in fact are the edges of the plasma, because that is where the visible light is emitted. In the center of the plasma, where it is densest and it is hottest, you no longer emit visible radiation, so it's sort of a naked plasma. You can't see it with the naked eye. But we have plenty of plasma diagnostics that will measure those properties for us. Now, in comparison, the W7X stellarator, which is in Greifswald, uses superconducting coils. So the pulse lengths that we can operate in W7X are significantly longer because of this. W7X is the world's most highly optimized and best performing stellarator. So W7X just broke records in terms of stellarator performance. And you can see that this machine, although it is also a donut, is considerably different from the tokamak. So W7X, the maximum pulse length that we have performed so far is 8 minutes. And the target for this device is to do 30-minute pulse operation, which is long enough to demonstrate that all of the systems are in steady state, and that one, in fact, could build a reactor concept from the superconducting and all of the technical systems needed to support it. So here's an example of a W7X plasma to give you an idea of what these look like. You can also have a view inside of the machine here, and you can see that the walls of this machine are also considerably twistier than in the tokamak concept. And over here, you can see that the pulse length, in this case, this is 30 seconds. It's significantly longer than what we can do in ASDEX upgrade. And what's really nice here is if you look at all of these time traces, all of these measurements as a function of time, they are incredibly boring. And that's exactly what you want in a reactor. You want things to be as boring as possible. You never want anything interesting to ever happen in your reactor. So this is also very good. Now, this concludes my section on how do we create fusion on Earth. Before I continue with my final bit, I want to do a quick recap of what we have learned so far. What is fusion? Fusion is the merging of light elements to form heavier ones. What is the difference between fission and fusion? Fission is when you break apart a heavy element to form lighter ones, and that process has radioactive waste that is considerably nastier, and it also has dangers such as chain reactions that can happen, critical mass, that simply don't exist for a fusion reactor. Why do we need fusion? Nuclear energy is more efficient than fossil fuels, and it does not have the same problems with respect to greenhouse gases. Moreover, analyses of energy supply and demand show the need for reliable baseload supply to fill gaps and provide grid stability. At the moment, we do this by burning fossil fuels and fission, and in the future, we think fusion is a great candidate to take over that role. How do we create fusion? Via the magnetic confinement fusion concept, we create strong magnetic bottles called tokamaks and stellarators to confine hydrogen plasma and heat it up to 200 million degrees, at which point in time, fusion reactions start to happen. And this brings me to my final question: where are we on the path to a reactor? And here I will focus only on tokamaks in the interest of time. So, for a fusion reactor to be successful, you have to produce more energy than you put into it. This is an obvious statement, and yet it is tricky to do. The ability to produce fusion power with a fusion reactor can be measured by the so-called triple product, NT tau. This is the product of the particle density times the particle temperature times the energy confinement time. And I show exactly this product as a function of energy here. And in order to have a reactor produce more power than you put into it, it has to get NT tau above this red line. That corresponds to what we call a capital Q equal to 1, or break even. And then, if you get the plasma to a completely burning state, then you don't actually have to put any more power into it. It will self-heat. And this is what we call ignition. This would be the green line. Now, you don't actually have to get to the green line to produce power. What you need is something between the red and the green line. Now, looking at these curves, you can see that there is an optimum temperature at which you want to operate the reactor. You want the temperature to be about 200 million degrees because that's where this curve has a minimum. That's where it's easiest to get the fusion reaction to happen. So that's your temperature. And then, based on the strength of your magnetic field, that dictates the maximum density that you can confine in your reactor. So you have no freedom in density either. And what you're left with is tau. You need to make your energy confinement time as large as possible. Now, what is this energy confinement time? You can think of it in terms of a cup of coffee. You pour your cup of coffee in a mug, you leave it on the countertop, and you come back to drink your piping hot coffee 10 minutes later, except it's cold. So your coffee cup has an energy confinement time of about 10 minutes. On the other hand, if you were to stick your coffee in a really good thermos, that could keep your coffee hot all day. So that thermos maybe has an energy confinement time of 10 hours. And this is very similar for a fusion reactor. It's all about how good you have made your magnetic bottle. The better the bottle, the higher the tau. Now, we can plot the success of individual tokamaks on this plot. And what you are basically looking at here is a history of tokamak research. These T3 devices down in the left-hand corner, these were the very first tabletop tokamaks that were built in the 1950s in Russia. And then as a function of time, over the last 50 years, we have gotten better and better and better at building our magnetic bottles. And right now, modern tokamaks, in fact, have reached break-even conditions. We regularly operate modern devices in temperatures in this range and with densities in the correct range. And while they are lacking, it's about a factor of 3, 4, 5 in energy confinement time and away from being net energy producing. And this is okay, because modern tokamaks were not designed to produce energy. They were designed to do research to figure out, how do I build a reactor that produces energy? And they have been hugely successful in that mission. Here I'm showing all of the energy confinement time data from all of those tokamaks on the y-axis, and this is an empirical scaling on the x-axis. And the data combined from all of these devices have enabled us to understand how energy confinement scales with things like plasma current and machine size, such that we can design a machine. In this case, the star I have here is ITER, which is being built in the south of France. And it will be one of the first tokamaks that produces significantly more power than goes into it. And I have one additional caveat that I wanted to mention here, but I think I'm running late on time, just to say this is empirical data, but we now have physics-based understanding of that data that supports these predictions. So, ITER. ITER is being built in the south of France. It has a major radius of 6 meters. It will carry a plasma current of 15 megaamperes, and it will have a pulse length of 400 seconds or 8 minutes. It is a superconducting device, and it will produce 500 megawatts of fusion power, having only 50 megawatts go into this thing. So that is a factor of 10 amplification in fusion power. It will first come online in the 2030s. Now, ITER teaches us some very important things about plasma physics that we need to know to build reactors and really predict how well they're going to perform. But one of the most important things that ITER has done and continues to do, it has taught mankind how to build a machine of this complexity on this scale. This becomes the blueprint upon which every other fusion reactor is going to rely to learn how to build those devices. People complain that ITER is behind schedule. Well, yeah, it's not really surprising that when mankind set out for the first time to build the most complicated device we have ever attempted to build, that maybe we had to learn some things along the way, and you're only ever going to learn them by doing. So in my opinion, this is exactly what public funding research should be all about, to teach us how to do these things such that we can have the next steps and learn from this to build the first reactors. So I'm getting very close to the end, I promise. I know I'm over time. This is a picture from 2018 from the ITER site. This is just to show you that it exists and it's being built. And I specifically chose an old image because the building wasn't done yet. So you can look inside of this building right now and you can see where that machine is going to be built, where it is presently being built. If you look at a picture of the ITER site right now, it's much more complete than this, but you can see a lot less. The buildings are closed. So here's a view inside of the tokamak pit where this machine is actively being assembled. Here's a little guy for scale so you can see how big this machine actually is. If you are ever in the south of France, I highly recommend going down to Cadarache and taking a tour because they do tours and it's absolutely amazing to see the progress on this device. Okay, I'm going to skip this slide in the interest of time. We're going to come here and I will say that ITER is still an experiment. In order to have a pilot plant, it has to do two things that ITER will not do. A pilot plant has to put electricity on the grid. ITER will not do that. It'll produce power, but it won't collect it. So you need to have a closed cycle where you produce electricity. In my opinion, it could be 1 megawatt. I don't care. I'd prefer it to be 100 megawatts or 500 megawatts. But if you have one, I think that's a huge success. And the second thing is it needs to close the fuel cycle. It needs to show that you can have self-consistent, self-fueling tritium production so that you produce your own fuel. And that's what the next generation after ITER has to demonstrate. And there are public and private programs around the world that are targeting doing just that. Here are two examples of public programs. There's the STEP program in the United Kingdom, and there is a program in China with the CFETR machine that is targeting on doing both of those things. So this is my last slide. This is just to show you that I've been talking about the core of the reactor. I've been talking about that plasma in the middle that produces neutrons that produce that net energy. But that's just the engine. The engine is a necessary element, but it is not sufficient. You need also the wheels and the seats and the steering column and everything else that goes with it to have a complete product. And every box here is a system that has to be developed for successful fusion reactors. And there are solutions and ideas for every single one of these, but because we have never built a fusion reactor, they have never been integrated together and to form and to test them in an integrated manner. And they're never going to get integrated unless we build. We have to build. So this brings me to my final slide. I won't go through all of this again. I will just come to my last point. Where are we? We know how to do it. We know how to build these burning plasmas. We know what we need to achieve in order to have net energy production. But there are still open physics technology questions and integration challenges that can only be tested if we build. So. Sorry for going over time.
Okay. Grazie alla professoressa McDermott. Abbiamo ascoltato tutti con grande attenzione questa spiegazione e credo che ci siamo fatti una prima idea di quanto grande sia questa impresa. Non a caso lei ha usato la parola challenge, è una grande sfida teorica e tecnologica. E in attesa di sentire qualche domanda, io vorrei chiederle, lei ci ha fatto vedere l'esperimento ITER che è straordinariamente impegnativo e grandioso con queste immagini così spettacolari e quindi si suppone che fra circa 10 anni dovremmo avere la prima accensione di questo plasma. Però quanto dovremmo ancora aspettare invece per vedere dell'energia prodotta e vedere una lampadina che si accende grazie a ITER?
Okay, so the very next generation of devices that are being built, ITER, for example, also the spark reactor in US, the BEST machine in China. These are machines that are targeting burning plasmas for the first time. So those are devices that are demonstrating that plasmas can produce more energy that goes into them. And this is an absolutely essential step. But those three machines that I just named will not produce electricity. They are demonstrators that you use as stepping stone to make sure your reactor designs will work. And one of the key differences here is that a machine like Spark that is being built in the US, this is already several $billion. But when you are talking about a reactor, now you're talking about tens of billions of dollars. So before you build a reactor, you want to be pretty sure that you are spending your money wisely. And this is why you have generally that step in between, that you are sure what you are doing. And most, at least in public programs, the timescales for building those reactors are 20 years. They just take a long time to break ground, to do the assembly, to do the procurement, to establish the heating systems, the diagnostics, the control. Private companies are pushing to increase those timescales. And in fact, some of these private companies have been quite successful at increasing timescales. And this is because I think anybody who works in a public sector knows that public sector in the West tends to be a little bit slow. When you're dealing with taxpayer dollars, there are a lot of rules you have to follow, and that just takes time. If you are a private company, you can spend money faster. And so they have been faster at breaking ground, at building buildings, at setting out contracts, at giving bids to the person or company best capable of meeting that bid and not necessarily the cheapest, which is something that the public sector always struggles to do. And so private companies have been successful at accelerating timelines. It is too soon to know if they will be really successful in accelerating reactors. But they also are targeting 10 to 15 years from now for the first pilot plants.
Ecco, e di che cifra stiamo parlando all'incirca? Quanti miliardi ci vogliono per realizzare questo prototipo di reattore?
Most numbers come in around 20 billion for a machine. And I could imagine if it takes 20 billion and it happens over the scale of 20 years, that 20 billion due to inflation could increase. It's 20 billion of today's dollars if you could spend it all today.
E quindi parlando di questa sfida appunto scientifica e tecnologica, credo sia inevitabile chiedersi chi è più avanti in questa corsa, se l'Europa, gli Stati Uniti, la Cina, chi è che si sta dimostrando più forte e che ha più visione?
There is a lot of scientific leadership in Europe. There are, to be fair, there are many countries around the globe with excellent fusion programs. With respect to ITER, which is an international program with partners all over the world, I would still say that there is a lot of leadership in Europe for that program right now, probably also because ITER is being built in France. But there is a very hard reality that we face right now, which is that programs, for the most part, in the Western world are not investing in fusion and fusion technologies at the same scale as, for example, being invested in China. The Chinese program is extraordinary. They are investing people, they are investing money, they are investing time. And they are building and progressing at a rate which is very hard to compete with in the Western world. So right now, I would still say that there is significant engineering and technology leadership in the West, but I see that flipping in the near future. And right now, China is learning from ITER. But at some point, they are going to surpass that, and we will be learning from China.
Ecco, e credo che sia inevitabile chiedere, visti i tagli alla ricerca scientifica dell'amministrazione Trump, se anche i programmi per la fusione nucleare sono stati già toccati dai tagli di Trump ai fondi federali.
Yes, that is true. I think a lot of the impact on the US programs is still not clear. There's still a lot of uncertainty for many individual programs. Will I have funding? Will I not have funding in the coming years? And that uncertainty itself is a big problem. If you are a postdoc, you are wondering, do I have a job next year? If you are a PI, you're wondering, can I hire a student next year? So at the moment, I think the impact is not yet clear, but the uncertainty is a very big problem for planning and for education and for those students. On top of that, in the US, they have a different balance at the moment between the public and private sector, where the private sector is taking on a much bigger leadership role in the US as compared to Europe right now. And that also significantly is changing the dynamic. And I think the public sector in the US is still trying to figure out how to engage with the private sector. This is something very new for us. And that's something we're starting to see also coming up in Europe and in UK. And you also start to see private companies in Japan, in Korea, and China as well. So that's something that maybe started in the US but is spreading.
Io intanto guardo se c'è qualche domanda dal pubblico. Ecco, vedo una mano, possiamo sentire il signore.
Grazie della spiegazione, quindi io ho capito che noi adesso abbiamo la tecnologia della fissione, lei ci ha spiegato la tecnologia della fusione, al momento la tecnologia della fissione prevede l'uranio, un passaggio intermedio tra la fissione e la fusione non potrebbe essere la fissione tramite torio. Cosa ne pensa di questa tecnologia?
Thorium. I'm not sure I know what thorium fission is.
Reattori a fissione che utilizzano torio invece che uranio.
Ah, okay, but this is still a fission process. Okay. I don't have a comment on alternative fission fuels. I'm afraid that's really not my area. I could talk about alternative fusion fuels. I'm sorry, I don't have an answer to that question.
Ecco, c'è una domanda qui. Prego.
Good morning and thank you very much for your interesting, very clear. Grazie mille per la sua presentazione, molto interessante. Io avrei un follow-up dal commento che ha fatto poco fa sulle compagnie private. Fino negli ultimi anno e mezzo si è sentito veramente un hype di società start-up americane che fanno degli accordi Power Purchase Agreement con le big tech. Se non sbaglio la compagnia Helium ha firmato un accordo con la Microsoft per iniziare a consegnare energia da fusione dal 2028, che è da qui a un paio d'anni. Io capisco il suo commento sulla differenza tra pubblico e privato, questo è chiaro, però dal mio punto di vista mi sembra che questo sia un hype commerciale o marketing per aumentare la valuation di queste start-up. Volevo chiedere un suo commento se stanno praticamente buttando fumo negli occhi o se veramente queste start-up nel giro di pochi anni possono avere dei prototipi che veramente funzionano, perché 50 megawatt sono tante, e se sono basate sulle tecnologie che ci ha spiegato lei oppure se è totalmente una nuova tecnologia di cui oggi non abbiamo parlato. Grazie.
I perfectly understand your question. There is a very wide range in startup companies, from extremely credible companies that have a very strong physics basis. There are also companies that are selling magic without any physics basis. So as an investor, it is extremely important to be doing some due diligence here and seeing if it is just a hype, a company that has formed to try and make a quick buck, who are promising things that can't possibly happen. There are many fusion startup companies that have concepts that people tried 50, 60, 70 years ago. They have been demonstrated in laboratories. They have been shown not to work. We understand why they don't work, but it was so long ago that we have forgotten that we actually have generation changes where companies are now proposing ridiculous concepts, and it is our retiring professors who are going, wait a minute, we tested that one. That one doesn't work. We know that one doesn't work. And so we actually have groups of retired scientists to some degree who sit down and evaluate these concepts and try to provide advice for governments and investors on what is a credible concept and what is not. Because you are correct, there is a big hype, and there are a lot of companies that, whether intentionally or not, are selling a product that they cannot fulfill on those promises. And if they are promising fusion energy on the grid in 2028, I can tell you they're not going to fulfill that promise. On the flip side of that is there are a number of credible companies who have maybe not completely realistic timelines. If you are a pessimist like me from the public sector who is used to dealing with public money and knowing how long it takes to spend public money, they are much more optimistic how quickly they can get things done. But in principle, what they want to do is perfectly legit. So there are quite a few companies who have absolutely credible lines to building power plants. My main complaint is that they are too optimistic on the timelines, because investors don't like to hear 15, 20 years. And so it's a balance between getting private investors on board and coming up with realistic time plans, how quickly you can actually build these devices.
Quindi mi pare che stia descrivendo una situazione che è abbastanza simile a quella delle tecnologie quantistiche e della realizzazione dei computer quantistici, dove da una parte c'è una ricerca pubblica e accademica e dall'altra ci sono il big tech e anche una serie di start-up che periodicamente fanno annunci molto enfatici sui successi che hanno raggiunto, ma non sempre questi annunci poi corrispondono a dei risultati pratici.
Yes, I think that's a fair description. I think it's a very similar analogy. What's interesting for us is this is the first time it's happening for us. So we have finally gotten to a point in the fusion community where building reactors starts to really look possible. And so for us, this boom of private companies with all of these promises is really rather shocking. It's said, oh my goodness, we've never seen this before.
Prego il signore.
Thank you very much for that, and I wish success to you and to the whole community in this super important effort. I wonder, in case the technology, the science, the technology, and the timing would all work pretty well, relatively optimistically, what is your estimate of what is known about the economics? I'm guessing that if we'll be producing, 5 gigawatt with a $20 billion investment, the cost of electricity would still not be competitive, even if we could do it in 5 years' time or in 15 years' time or whenever. So what can you say about that aspect?
There have been quite a few studies that are working on that, and I don't think anybody has a final answer. Also because if you look at the studies of what is going to be the price of energy with the energy sources we already know, with the solar, with burning of fossil fuels, etc., you get huge variation in the economic projections. And so adding fusion is now an additional variable, and the uncertainties are going to be correspondingly large. So the size of reactors that you are looking at, the designs are targeting between, say, 100 megawatts and 500 megawatts electric. So that's sort of the size of the electricity production that you are looking at in fusion reactors. And when you combine these with other mixes, especially mixes with a significant fraction of renewables, it's actually not too bad because you have it as a mix. Whereas if you were trying to produce 100% of your energy with fusion reactions, it's going to be significantly less economical than if you are trying to use this to supply a 10% or 20% base load. It actually gets offset by being a piece of the mix. But I think that the basic answer is we don't yet know, and projections have big error bars, but the most recent studies are looking at it being comparable in cost to other forms because of how it gets incorporated in a mix and because of the geography of where you can build these things and how you're limited in where you can put your solar and your wind. I think we need a little bit more time on that, though. But people are working on it, I can say that.
C'era qui e poi la signora.
Grazie per la spiegazione. Mi interesserebbe sapere qual è la percentuale dell'energia elettrica che si può produrre dal raffreddamento dei neutroni che colpiscono il blanket che copre cioè che permette quindi anche la formazione del trizio, e quanto è urgente la creazione di energia grazie alla fusione nucleare per creare anche l'elio in quanto elemento sempre meno disponibile ed essenziale per diversi macchinari con applicazioni anche in ambito medico.
Okay. So my translator was saying she was having trouble understanding you, so I'm not quite sure what the question was. You were talking, though, about the energy production from a fusion reactor. So you have the 14 MeV neutrons that are going through the walls, that are going through the blankets, they're being slowed down, and the energy from those neutrons is heating up. It depends on which concept one is using, but the energy is taken from the neutrons to heat up some kind of a working fluid, and then it is extracted from those blankets via heat exchangers, and then it becomes very standard technology for producing electricity. But there is a second component there that I think you were referring to, which is the direct heat. That, in fact, the walls of the reactors, the diverter components, all of that will become potentially quite hot just from being in vicinity of this burning plasma. And people are looking also at heat exchange from those wall components for energy production. But you do need a very sizable difference in temperature in order to make that process efficient. Is that what you were asking? Sorry.
Overall the energy which is su tutta l'energia che è prodotta dalla fusione nucleare per la variazione della massa, qual è la percentuale dell'energia elettrica prodotta per il raffreddamento dei neutroni e quanto può essere utile un reattore, cioè la fusione nucleare per la creazione dell'elio, che è sempre molto utile in ambito biomedico e che è un elemento sempre più richiesto e anche sempre meno presente nelle risorse sulla Terra.
Well, in principle, we do produce helium. That is one of the byproducts. Now, how much helium do we actually produce? I would have to crunch some numbers to see if this makes at all sense as a helium supply. So in principle, yes, absolutely, reproduce helium. Helium can be separated in the gas from the gas that gets pumped out of these reactors. In principle, it could be produced as a product. What I don't know off the top of my head is if the quantities of helium make any amount of sense for one to do that. We could check it out. It would be easy to calculate. It wouldn't be hard to figure it out at all. Next time for my physics class, I'll have my students do it and report next time.
C'è un'altra domanda? Ecco qui, era questa signora qui.
I apologize for not being so optimistic, però quello che voglio chiederle, io sono stato il mese scorso a visitare ITER e chiaramente c'è dietro una visione ottimistica dei rapporti mondiali, una visione che mi sembra oggi molto problematica. Quando si arriva in ITER si vedono le 25 o 30 bandiere che tutti cooperano in maniera straordinaria. Reggerà ancora nei prossimi anni questa voglia di cooperare?
You know, I skipped that slide. That was the slide that I skipped. So you are correct. ITER is an international partnership with many, many countries that came together to try and build this. So many countries are involved in the ITERs. They deliver components for ITER, in-kind contributions. And this was wonderfully optimistic. This was wonderful politics 30 years ago when people came up with this. And everyone said at the end of the ITER project, every ITER member state is going to have the technology and the know-how to build their own ITER. Isn't this a wonderful thing? And it is a wonderful thing if it would really work out that way and possible. But it also made an absolute nightmare of project management for ITER. Many of the ITER delays are in fact due to how the management and the financial structure of this project were created. Now, what I will say right now is that within the fusion community, we still work together quite well despite political tensions. We try very hard to keep science and politics apart. We have colleagues from Russia. We have many colleagues in China, and we, on the ITER project, in these international experiments that we do together on this fleet of tokamaks around the world, work very closely with our partners in all of the ITER nations. So yes, the politics is starting to influence things. It has not yet influenced the science. Could it? Thank you. Could it? Yes, there is a danger that it could. For example, just last week we had the IAEA Fusion Energy Conference in China, and because it was set in China, the United States colleagues got instructions not to attend. There was not a single scientist from the United States that was allowed to attend the conference in China, and that is a shame, because politics should not influence science. We also have had to start adapting. We have more meetings at the ITER site, and we have more meetings in Vienna at the IAEA than we used to have. Because if we have them at those sites, it enables all of our international partners, including partners from Russia and from China and the US, to all get together and attend in the same place. And so it has started impacting how we work. I think ITER is far enough along, and the promises of the component delivery are sufficiently far advanced that I don't think it shouldn't directly impact the ITER project, but it certainly is impacting all new projects that start now in terms of how we are thinking about supply lines and supply chains and how do we procure which components. We are turning to new vendors for things where we think economically we're going to have problems either with Chinese or Russian vendors. So it certainly has an influence, and I'm not willing to give up yet, but you are not wrong. It could impact the research in years to come. It could impact how we go about building these things and how we build supply chains.
Ecco, c'era una domanda qui che era in attesa, per favore. Possiamo sentire qui? Allora là, va bene.
So, thanks a lot for your presentation. Okay. Grazie mille per la sua interessantissima presentazione. Avrei un paio di domande. Innanzitutto, per quanto riguarda la produzione di altre forme di energia tramite fusione nucleare, a partire dal calore e soprattutto dalla generazione di energia elettrica, un potenziale reattore quanta ne potrebbe produrre rispetto a un reattore a fissione alimentato da barre di uranio? E seconda cosa, siccome servono elementi per andare a generare per dire del trizio e così via da impiegare nei reattori a fusione, in termini di supply chain, quindi a livello puramente geopolitico, come siamo messi sotto questo punto di vista e anche come siamo messi dal punto di vista degli impatti derivanti dall'estrazione di questi elementi?
Okay, that was a lot of questions. Okay, so one of the most ambitious reactors plan is the EU demo project, which was aiming to produce 2 gigawatt fusion power with 500 megawatts electric. This is probably the biggest fusion power plant design that I know about, and that puts it roughly equivalent to sort of medium fission power plants. And I think you could also imagine smaller scale, that you say I have a fusion power plant that produces 100 or 200, 250 megawatts of electricity, depending on what exactly you are using it for. So it varies a little bit. You probably will not be looking, at least not in the first round of fusion reactors, you're not going to be looking at bigger plants than that. So in that sense, you could probably still have fission reactors that would produce more, but the tendency in fission reactors right now is not to build big fission reactors. People are rather looking at smaller city-scale fission power plants as adding those to the mix when they're looking at building new fission reactors at all. And in that sense, it becomes actually quite comparable. Okay, I think that was the first question. The second question was about materials. So lithium is an excellent example of this. Most of the lithium handling actually goes through China at the moment. They dominate the market with respect to China. And there are just a few other places in the world, in South America, for example, that are starting to step up lithium production and lithium enrichment. And this is a potential big supply chain issue going forward. And in general, lithium technology and lithium handling is somewhere where we could use significant technology development. So one thing I did not mention in my talk was the difference between lithium-6 and lithium-7. And what we actually really want for fusion is lithium-6, which is not the dominantly occurring isotope. So in order to have a net tritium breeding ratio greater than 1, so that you have net production of tritium, you need enriched lithium. And there are lithium enrichment technologies being developed all over the world, including in Europe, including in Germany. And this is, at the moment, an active area of research. I think we do not yet have those capabilities that would supply that I want to say food chain. Food chain is not right. Supply chain. That we don't have the supply chains 100%, but there are economic projects being started in many countries. The United Kingdom is a prime example of that, where people are actively looking to build supply chains in support of future fusion reactors and trying to do those economic studies. And there's a group in Europe doing the exact same thing, How do we identify those materials? How do we procure those materials? How do we scale up the production of those materials on a 20, 30, 40-year timescale? So it doesn't exist now, but yes, there are groups actively looking at that and working on it, and lithium's a prime example.
Abbiamo ancora una domanda qui. Vabbè.
Sì. Una questione veloce a proposito di tecnologie che ritornano dal passato, i cosiddetti processi di fusione Z-pinch, come quello proposto dalla startup statunitense Zap Energy. Volevo sapere cosa ne pensava e se era effettivamente una terza via possibile per l'approccio alla fusione. Grazie.
I try very hard not to make openly negative statements about individual companies. I will say, I showed a video earlier in my talk where we bent magnetic field lines into a circle. We bent them into a donut shape, and there is a very good reason why we did that. We need those particles to be trapped. You need them to go around and around and around and stay confined. And any magnetic configuration that is not closed on itself, it has open field lines that terminate on surfaces or chambers, you will lose particles out the end. And it is it's not even extremely difficult, it is impossible. This is plasma physics 101. It is impossible to build up sufficient temperature gradients parallel to magnetic field lines to reach that 200 million degrees in the center, because the heat conductivity of your plasma will go as the temperature to the 5/2. So the hotter you get it, the faster it flows out. And any configuration that uses open magnetic field lines will not be successful.
Grazie. Purtroppo il nostro tempo è finito, quindi ringraziamo la professoressa Rachel McDermott. Grazie. E penso che avremo ancora molte altre occasioni per parlare di questo tema così affascinante, visto che abbiamo molti anni ancora di fronte a noi. Grazie. Grazie.
Thank you.